All right, good morning. Wow, yeah, 5 people. I'm also surprised there's not more people. There's not much to do to the day after a PA is due. Yeah, except heaps and heap sorts and heapification and a preview of dynamic programming, which is the foundation for PA5. So, thank you for being here. Let's see. Spend the whole class talking about what people did wrong. No, I'm not going to do that. Totally had to take an L on PA4. The darn delete function got me. I'm less concerned about the grade, more concerned about how to actually do it. Yeah, so it's 20 points if you turn it in a day late, which, if none of PA4 is working, it might be worth, taking that option. But delete, I think, is only worth 15 points total, up to you. But yeah, it's good to figure out the delete function. And next week we're going to talk about balancing binary trees. Also, we're not going to. I don't think I'm going to have you code that for grades, but that's another fun algorithm along the lines of deletion, right? Keeping track of things and moving things around and patching up your tree accordingly. So we'll play with that next week. So I'll probably make PA4 comments on Monday because, I need the weekend to go through and test them and look at code and things like that. So probably not a lot to say today on PA4, but we'll do some wrap up on that on Monday. So any questions? All right, so as usual, that's either really good or kind of a problem. I'll assume it's really good. All right, so let's continue playing with heaps. So remember the basic setup for a heap, 2 properties. Oh, question. Okay, can you go through delete one time real quick? Sure. Let's do tree deletion. So the whole trick is deleting the root of a tree, right? If you're not deleting the root, then you're going to delete from the left or right subtree, and you're going to say something like, if data is less than root data, then you want to delete from the left subtree, so you're going to say root left equals delete root left, comma data. So the usual recursive game playing that we do to call your delete function. So the real effort is deleting the root. And so to delete a root, we do the following things. First, we find the largest node in the left subtree. So look to the left of the root. Just treat that as a binary tree on its own, and find the largest item in there. So in this case, it's going to be an 18. How do we know that? Start from the root of that tree and just keep moving to the right. Go as far right as you can. When you can't go further, that's the largest node. Okay, and now we do 2 things. 1, we make 18 the new root, and 2, we have 18's parent adopt 18's left child as its new right child. So 18 is going to be the root. How are we going to do that? We're going to set 18 left equal to 20 left. We're going to set 18 right equal to 20 right. And before we get rid of our reference to 18 left, we're going to have 18's parent and set that thing's right child equal to whatever 18's left child is. So if this is, root, and this is our left root, and this is largest, and this is the node prior to the largest, then we can you have to do some work to move down to the left root, move to the right. But once we've done that and we have these temporary variables pointing to these nodes in our tree, the deletion is a few lines of code. So it's something like previous right equals largest left. That changes this so that the left child of largest is not going to be orphaned. And then largest left equals whatever the root currently has on the left. So that sets this up to point there. And then largest right equals root right. And so on the right, we pick up all of the stuff that was to the right of the 20, and then free node root, which gets rid of that storage and the strings that were allocated inside there. So there are edge cases, and a lot of this works automatically. If there's nothing to the left of largest, then this is just going to set previous right equal to null. That's perfectly fine. If there was nothing to the right of root, this would set largest right equal to null. That's perfectly fine. But the two edge cases you do need to worry about is one, when you're trying to find the largest node and the previous node, there may not be a previous node. You could have a situation where you look at something like this. And so you come down here, and this is the root of the left subtree, and you're going to start moving right to try to find the largest node. But this is the largest node. There is nothing to the right, and so we don't have a previous node in this case. So this code won't work in this setup. You need to handle this as a special case. So basically, in the beginning of all of this, you said left root equal to root left. Check to see if there's anything to the right. If there is, start marching down, keep previous largest. If there's not, then we have to do something special. And what do? We basically just change this to be the root. So it will keep its left child, right? And it's really just largest right equals root right, and free the root. And then the other special case is when there is no left subtree at all, when the left subtree is null. And in that case, we just change the root equal to root arrow right, and we free node the root. So this is the one where you do the most work, but it's also in some ways the most straightforward. Once you've moved around the tree and figured out where previous and largest is, and then you go ahead and you set those up. So if it's still seg faulting, try to find a simple test case that makes it fail, so you don't have to insert 500 things first. Try to find the simplest test case you can that will expose the seg fault. And then right before that, take a look at your tree. Make sure your tree is a properly formed BST. And then just start stepping through your code. And it might be seg faulting when it tries to move through the left subtree and find the largest node. Or it might be seg faulting when it tries to patch something up. Or, worst of all, it's seg faulting later on, right? It comes back from delete and it's like, I'm all done, and then somewhere down the road you try to do a traverse or a search and it seg faults, right? If that's what's happening, what you want to do is after you come back from delete, go into your tree in memory and just look at it, right? Look at root arrow left, root arrow right, root arrow left, 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 right, and so on. Draw a picture of your tree, and chances are you've got something pointing somewhere that it shouldn't. and then later on when you try to do an add or a search or a traverse, that null pointer or invalid pointer is coming up as a seg fault. And as usual, office hours, we can work on this together. All right, other questions? All right, so adding and removing in heaps. So remember, heap is a binary tree with two properties. It's shaped like a heap, and each node satisfies, for us, we were talking about the max heap property, which means each node is bigger than its children. And so let's start with a heap. Alright, so there's a heap. It's shaped like a heap. It's full on every level except the last one. The last one's filled in from left to right. And each node is bigger than its immediate children. So that's a max heap. And so if we want to add a number, so let's add a 35. The process is two steps. First, put that 35 in the next position that preserves the heap shape. So it's going to go on the lowest level, leftmost spot that's open. If the lower level is completely full, it's going to be the leftmost thing on the next level. All right, so add it to the bottom of your heap and then up heap. So how do we up heap? Compare this new node's parent to its children, see if it satisfies the max heap property. 29 is not bigger than both children, so swap 29 with the largest child. So 29 will go here, 35 will go here. Now check 35's parent, see if it satisfies the max heap property. 30 is not bigger than both children, so swap 30 with the largest child. This becomes a 35, this becomes a 30. Now check 35's parent for the max heap property. 50 is bigger than both of its children. We're done. We finished adding 35, and we should have a heap still. All right, let's add a 45. So it's going to go over here, because that's the next position to make it look like a heap. And then check its parent. 28's not bigger than both children, so swap with the largest child. And then up heap again. Check 45's parent. 35 is not bigger than both children, so swap with the largest child. And then check 45's parent. 50 is bigger than both children. We're done. So at each point we insert the number into, the lowest level, leftmost position, and we up heap, and when we're done, we've got a heap back. So let me switch to read-write mode here. That's computer science lingo for pencil. All right, and remember the kind of punchline of a heap, a max heap in this case, is that the largest item in the heap is always at the root. So if we want to retrieve the largest item, it's always just the root. So typically what you're doing is you're getting data coming into your system, you're storing it in a heap, and at some point you want to remove from the largest to the smallest. So stacks are last in, first out. The last number that you put in a stack is the first one you remove. Queues are first in, first out. The first thing you put into your collection is the first thing that gets removed. Heaps are maximum in, first out. So whatever the largest thing is that you put in your collection, that's the next thing you're going to remove. And a min heap is like smallest in, first out. So I don't know, a MIFO and a SIFO maybe. Alright, so if we start removing from this, we want to remove the largest element. Well, that's our 50. And the way we delete, we remove the root and we replace it with the last thing in our heap. So lowest level, furthest to the right, that's a 28. So we're moving that up to the top. And then we do a process called down heap. And it's just like up heap, but it starts from the top and moves down. So how do we down heap? See if this satisfies the heap property. It doesn't. So swap with the largest child, which is 45. So 45 goes here, 28 goes here. Now down heap from here. This violates the max heap property, so swap with the largest child, which is 35. So 35 goes here, 28 goes here, now down heap from here. The max heap property is satisfied because it has no children, so we're done. We've got a heap again, the 50's been removed, and the largest thing remaining in the heap is now at the root. So what is the complexity of that? How many operations do you think that takes? Ballpark. So removing the root is order 1, right? Because we just, take the root of the tree, root arrow data. So it's this business of down heaping. Now we have to find, what the last thing is in the heap, and we'll talk about a nice way to do that. But, making that the new root, so set its left and right. And this won't have any children, right? Because it's the last thing in the heap. But then this down heaping business, how many operations do we potentially have to do to down heap? It's actually better than order n. So if there's n pieces of data in here, right, and we down heap, well, how do we down heap? We start from here and we check the heap property. So we compare it to 2 children, and if it violates the heap property, we swap with the largest child. Okay, well, swapping, is a fixed amount of effort. This is node 1, this is node 2, so, node 1 left equals node 2 left, node 1 right equals node 2 right, node 2 left equals node 1 left, and node 2 right equals node 1. So that's a fixed amount of work. And after we've swapped, we've moved down 1 level, and now we have to check the max heap property there. So worst case, we're going to, check this node, find it violates, make some adjustment. Let's say that, we swap with this, check this node, if that violates the property, make some adjustment. Let's say we come down here, check this node, right? So in this case, we'd have to do 1, 2, 3, 4 rounds of this operation. But we have a lot more than 4 pieces of data in here. So this is basically bounded by the height of the tree, which is the depth of the deepest node. Well, what's the depth of a deepest node? We actually know pretty exactly, because this tree is guaranteed to be nice and full and fluffy, right? Every level is going to be filled in before we move to a deeper level. So this is actually going to be like order log n. In the same way that, searching a binary search tree or inserting to a binary search tree is order log n. Log n tells you how many levels there are to get to the bottom. And you know, when you're down heaping, you might stop somewhere before you reach the bottom of the heap, but worst case, you go all the way to the bottom. It's log n operations. So this is very efficient. All right, let's remove a few more numbers. Let's remove the root again, so that's a 45. We'll take that out. We'll move the last element, 29, up to the root. And now we start down heaping. Well, 29 is smaller than both of these, so let's swap the 29 and the 40. Put the 40 there, put the 29 here. Check the heap property. This satisfies the max heap property. We're done after just one operation. And the largest number in the collection is now sitting at the root. So if we remove again, we'll pull off that 40. All right, so that's insertion, that's deletion. And they're both order n, right? When you insert, we add to the last spot and we upheap. And again, the number of times you might have to upheap is bounded by the height of the tree, which is log n. All right, so what about building a heap? Suppose you have a set of data and you want to turn it into a heap. So one way to do this is to start with an empty heap and just insert a 12, a 15, a 5, 11, and so on. Just do all of these inserts. And each time that you insert, right, you add it to the bottom and you upheap. And each of those takes order n, order log n, and you have n numbers, so you can certainly build a heap containing n things in n log n steps. And the person who invented heaps, this was their approach for creating a heap out of a set of data, and it was n log n. But a number of years later, somebody found a better way to do this, and we can actually build a heap in order n. Right? We can start with an empty heap, and we can build a heap containing n pieces of data in order n steps. And this is really nice, right? This is better than we get with, say, a binary search tree. All right, and this is what we started to go down yesterday. So this is something called heapification. I don't know if that's an official word, I just like saying it. But the official term is to heapify. All right, so here's how we heapify. I'll do this in pencil too. You take your data in whatever order, typically the order it comes in, and you put it in a heap shape. Okay, not a heap. It violates the heap property lots of places, but it's shaped like a heap. Okay, so now the heapify process is as follows. We start from the last element, right? So lowest level, furthest to the right, and we're going to work our way backwards. So we're going to go right to left, and then we're going to go up a level and go right to left, and then go up a level, and so on. And at each number, what we're going to do is we're going to down heap. All right, so we're going to compare this number to its children and make any adjustments that are necessary. Well, this number 29, it has no children, so it satisfies the heap property, so there's nothing to do there. Same thing with the 14 and the 7 and the 11. Okay, so there's no work to do on this lower level. Now we go to the next level up and we start from the right and we look at the 5 and we say, does this violate the heap property? And it does. It's not bigger than both children. So swap with the largest child. So put a 29 there, put a 5 here, and now check this number. Well, that satisfies the heap property, so we're good. Now come over here, look at the 15. Does that violate the heap property? 15 is bigger than both children, we're good to go. Now go up one more level, rightmost value, look at the 12. That violates the heap property, so swap with the largest child. So put a 29 up here and a 12 down here. And now down heap from 12. 12 violates the heap property, so swap with the largest child, 14. Put the 12 down here. And we're done. There's our heap. And at first glance, we're working on n pieces of data in the heap. And at each one, we're doing a down heap process, and down heap is bounded by the height of the tree. So first calculation, this looks like, n log n. But it's actually kind of miraculous. So let me draw a heap shape. All right, we've got 15 things in this heap. We start off at the lowest level and we look at each of these to see if they violate the heap property. They have no children, so they do not violate the heap property. So we don't have to do any work on this lowest level. And how many nodes have we taken care of? 8. Half of our data we don't have to do any work on. So if you're starting with n pieces of data, half of those, there's no work to do. Okay, let's move up one level from the bottom. And worst case, every one of these nodes violates the heap property, in which case you have to swap with the largest of its 2 children. That's a single operation per node on this level. How many nodes are there on this level? N over 4. And for those n over 4, you have to do one operation. That's 3/4 of your whole data set. 75% of all your data in your heap involves either no operation or a single operation. In fact, if you average this out, the average is quite a bit less than one operation. And if we go up one more level, we've got an extra 1/8 of your data, and you might have to do 2 operations. And now we've done 7/8, right? 87.5% of your data has been processed, and you did either no work, 1 operation, or 2 operations. So if you work this out and you do the infinite sums, this turns out to be order n, which is fabulous. So it takes you n operations to build a heap, and then if you want to find the largest number in that heap, that's 1 operation, and it's log n to readjust the heap. All right. So this is what we call heapifying. And you can build a heap by just inserting, your data one node at a time. That gets you a heap also, but this is more efficient, quite a bit more efficient. All right, questions about that? That's a seriously non-obvious algorithm, I think. All right, so let's talk about implementing heaps. So they're binary trees, which means we can make a structure with a data field, a left and a right, and we can, set up left and right children to point to other nodes and so on. And we can use what we used with binary search trees. But there's some complications with that. One complication is when you're upheaping, you need to compare your parent. You need to check the heap property of your parent, right? If I've just moved something into this location, I need to go to its parent and see if that It satisfies the heap property. So we need back pointers to get to, our parents, whereas a regular BST, we always just move from the root down. So that's one issue. The second issue is this business of finding the last thing in the heap, which in this case would be right here, or figuring out where we should add something. What's the next place to add, which would be, right here. And that's a little tricky to do with a regular binary tree setup, because we don't even know if this thing is on the left or on the right. Now, if we record the number of nodes in the heap, we could do some kind of fancy calculation involving logarithms or playing high-low on binary representations or something. We could probably figure out how to get here. But, right here, the way I get to this next location is I go left and I go right and I go right. If I want to add another location after that, I'm going to have to go right, left, left. And so that gets potentially tricky. But it turns out there's a way to implement heaps that cuts through all of those details. And that's to use a good old array. So let's draw a picture of a heap. So there's a heap that's not quite filled in on the bottom level. And I'm going to make an array. And I'm going to put indices next to these. And I'm going to store in this array the contents of my heap from top to bottom, left to right. And I'm going to start at index 1. So if you hate index 0, this is your chance to party down. So my data is just going to be stored like this. And I'm going to keep track of my heap size. I'm going to set it equal to the number of things in my heap, which will also be the index of the last thing in my heap. Okay, so where is the root of my heap? It's always at index 1. So that's easy to find. Where is the last thing in my heap? It's always at index heap size. And where should I insert a new thing into my heap? It's at index heap size plus 1. And so to add something new to my heap, I basically increment heap size, and I just store at that index in my array. So if I want to add an M, I'll change my heap size to 13, and I'll store my M at index 13. So now we don't have to worry about, figuring out where the last node is. Should we go left or right at Albuquerque and so on? It just goes into, the next spot in the array. All right, now let's make a table with some samples. Let's look at node E. So E's index is 5. So what is the index of E's left child? It's a 10, right? E's left child is J. J is at index 10. And E's right child, right, it's right next door, that's at 11. Let's look at node C. Index of C is 3. What's the index of its left child? It's Friday. Yeah, I know. All right, here's node C. C is stored at index 3 in our array. Its left child is F. Where is F stored in the array? What index? Awesome. F's index is 6. And what about C's right child? That's its index 7. Its right child is G, and G is at index 7. Awesome. All right, let's do one more. Let's look at node D. So what is D's index? That's at index 4. D's left child is 8. What's the index of that? All right, go for it. Index of the left child is 8. Index of the right child. So this is where I need the SpongeBob dollars I can like hand out. Come on, fame and glory here. Right child of node D. What's the index? 9. There we go. All right. What's the pattern here? In general, if I have a node with index n, what's the index of its left child? Yay, brownie points. What are brownie points anyway? Do they get you brownies, or is it from being a brownie? Right? If you have a node with index n, the left child is always at index 2 times n, and the right child is at index 2 times n plus 1. Perfect. So we can move around our tree, which is a heap, by just doing simple arithmetic. Right? We're always going to start with the root that's at index 1. If we want to go to the left, that's going to be index 2. If we want to go to the right, it's going to be index 3. If we're at index 3 and we want to go to the left, that'll be 6. If we want to go to the right of that, that'll be 13. If we want to go to the right of that, that'll be index 27. So we can bounce down this heap really easily by just, either doubling our index or doubling and adding 1. So this is a really convenient way to store this information and let us move down the heap. Now what about moving up? Because remember, when we're upheaping, we need to know what the parent's location is so we can see if the parent satisfies the heap property. So if we're at node 10, 10's parent was 5. If we're at node 11, 11's parent was also 5. 6 and 7's parent is 3. 8 and 9's parent is 4. So take a shot at a formula for finding the parent of node n. N over 2. with the caveat that if n is odd, we want to just take the integer value. We definitely don't want an index like, 3.5, so you just truncate it. So if it's a left child, it's n over 2. If it's a right child, it's n over 2 minus a half. So just do the integer n divided by 2, and that gets you the parent. So if we're upheaping, right, if we just added node k, which was at index 11, and we want to check its parent, well, divide 11 by 2, that gives us 5, that's E, and compare 5 with its two children, who are at indices 10 and 11. C will round down for positive numbers. For negative numbers, I prefer not to think about it. But if I have an integer like 17 and I divide by 2, I'll get back an 8 as opposed to a 9. You can also right shift by 1 bit if it's a positive number, and that divides by 2 and rounds down. In fact, it's a quicker way to divide by 2 sometimes. All right, so plain old, CSE222 array of data, simple, arithmetic operations, and those let us do all the things that we need to do all of these heap algorithms. Right? We can find the root, its index 1. We can find the last node, its index heap size. We can add to the heap by incrementing heap size and storing there. We can find a child on the left or right with these formulas. We can find a parent with this formula. That's all you need, right? This is like so much fun to code. It's like, like a world caliber Olympic athlete playing on a trampoline at Gymboree or something like that. It's a fun little walk in the park, and there's no pointers, there's no mallocing, things like that, right? And arrays are fixed in length in C, but everything we do in the array is packed in here starting from index 1. And if we needed, to add more stuff than 14 things in our array, if we had a way to grow our array, none of this stuff changes, right? We just keep adding more things down at the bottom of the array, so you could do some kind of reallocation of memory or something like that. So this works really well. And heaps pop up inside operating systems. They're useful for a lot of things. One thing they're useful for is what's called a priority queue. So a priority queue is like job scheduling. So let me talk about this. So job scheduling, right? You have a CPU, it's shared by all the jobs on the system, or you could just make some massive array, yeah. So, here's job 1, here's job 2, here's job 3, and the CPU is executing job 1 for, a few milliseconds. And then when that time slice is done, it goes on and it executes job 2 for a few milliseconds. When that's done, it executes job 3. And when that's done, it goes back to job 1 and so on. And, maybe it's executing job 2, and at this point a new job 4 appears. And so after job 3, job 4 will get a slice of time. And maybe, it goes back to job 1 and job 2, and now job 2 finishes, so that gets removed from the queue. So now it'll do job 3 and job 4 and 1 and 3 and 4. And so, operating system does this round robin kind of processing of jobs. But these may be user jobs, and there may be, super user jobs that are higher priority. And maybe when job 3 is finished, 3 high priority jobs have appeared. And so now, instead of going on to job 4, it's going to go on to S1. And that's probably going to finish pretty quickly. And then S2, and maybe that finishes. And S3 gets a slice. And maybe it needs, multiple slices. And then eventually when that's done, it'll go on and it will go on to job 4. So typically in an operating system, we have multiple job queues with different priorities. And part of the operating system's job when it's time to start a new process is to say, okay, what's the highest priority job that's waiting to execute? And typically you would find something like a max heap being used to store this information, so that the operating system can quickly say, give me the job with the highest priority. And that's basically just pulling off the root. So that's one place where you'll see max heaps used in OSs. All right, questions about heaps? I might have to make a homework assignment, ungraded, to give people an opportunity to practice some of these things. Because probably on the exam I'm going to ask you to do some heap operations or answer some questions about heaps and so on. So I might put together some practice questions for those kinds of things, just to make this less abstract. All right. So that's pretty much everything I wanted to say about sorting. There's a lot more to the subject. You could spend a whole course probably just talking about sorts and searches. But that's, you know, a handful of sorts with some different characteristics. PA5, I've never done a PA on heaps. I don't think I'm going to. But that would be fun. PA5 is going to be about dynamic programming, and that's our next unit. And I will post PA5 on Monday, and that will be due the following Monday. So you'll have a week to do it, but it'll be due a week from Monday, because we're running out of time in this quarter. Or rather, the quarter is coming to an end quickly, which is cool. So yeah, next week is week 9. And then there's one more week after that. So I don't want you turning in your last assignment on the last day of class. So I'm going to make it due Monday. And we'll talk about that starting on Monday. But basically, dynamic programming is about recursion. And it's looking at algorithms that we can write a recursive algorithm pretty directly to solve a problem. But sometimes these recursive algorithms take a really long time to run. And so we're going to look at ways that we can speed up the behavior of recursive algorithms in order to make some of these problems practical. So we'll get into dynamic programming on Monday. All right. I'll post it on Monday. I have to write it first, but I'll post that on Monday or sometime this weekend. And we'll talk about it on Monday. But I got to grade PA4 first. All right, so have a good weekend. I'll see you in 2:15 if you're in there. If you did not submit PA4 in a way that let me access it, I sent you a note on Canvas already. So go ahead and take care of that and make it available by 8 a.m. tomorrow. Have a good one. I will see you next time.